Let's now build the first object detection model and then some basics of how to how to evaluate the performance of that object detection model. Okay, so very trivial model. Let's say I want to object detect the important objects here, which is cats and dogs. So what is the way to go about? Okay, so we already know how to set the problem up as we saw here. You need to have two heads, one for classification, one for box prediction, the bounding box coordinates prediction, and then you find the loss both of them, and then total loss, right? So the network we know, but how to build that network, right? The model architecture. So one trivial way is to basically use a sliding window. That's just slide it, and then each of these you crop it, pass it to a neural network, and give those predictions that we. So basically, take the entire image, crop it into small windows, use that sliding window approach, whatever you want, and then pass it through neural networks. But it's not that easy, right? Because the idea is good, but what is the window size? Shall I go for this window, or because this is good for this cat, but it doesn't fit the dog, right? So it doesn't help. So the window size is a variability here, and it's very difficult. What's window size is a problem, and how many such windows? So shall I go from top, then so many unnecessary background places I'm sliding it, so lot of complexity, unnecessary computation, right? And just to give a figure, you can put numbers and see what is this humongous number looks like. So let's say an image of size capital H cross W with a window size of small h cross W, total possible combinations, if I want to exhaustively do something like an iterative greedy algorithm, this is the total number of combinations. It's a huge number, and that's unnecessary calculation most of the time. Okay, so what is a better idea? The better idea is trust your old friend, classical image processing. None of you might have studied that, but there are so many effort done in last 100 years or so. Classical image processing plus machine learning, something like singular value, something like support vector machines as a classifier on a classical image processing. So you can rely on such techniques. So we are going to rely on one technique from literature, which is known as selective search. And what it does is it runs classical image processing on the image, typically image segmentation, and then use machine learning to reduce the number of uh, the segmented parts and come up with less number of segmented parts, and then use that segmented parts as your kind of bounding boxes to start with. Okay, so instead of sliding a window, this will give you some approximate windows to start. So it looks like this. So I took from this paper, you can actually see here, and then this will be a good link as well. You can click on this, and then this will help you understand this picture as well in better if my explanation is not clear. So what it does is it takes this and use classical image processing to generate tons of segmented regions from this can be based on color, this can be based on distance between certain regions, it can be based on edges, for example. So whatever you choose, you basically generate millions of segments from this image. Then if you put a bounding box, it looks like this. Pretty much everywhere you have a bounding box, not good. Then you do a machine learning on top of it, suppress some of these segmented regions or group them together into bigger regions like this, which we call in image processing domain, this idea is known as super pixels. You are grouping many pixels to form super pixels. So this grouping can be based on intensity or some other measure. Okay, so you have better result here, less number of bounding box, you can do few more iterations, and then you can end up in something like this. Okay, so what is this? These are the proposed regions where your CNN should now start looking into to kind of predict the bounding boxes. Okay, so those are kind of approximate location of your objects in the image. Okay, and just to give you an understanding again, so what we are doing here is over segment the image based on maybe color similarity or texture or size or shape, and then a linear combination of all these, and then pass it through a machine learning to come up with less number of initial seeding points. Okay, and this algorithm, which we will be using in the lab as well, so you'll be playing with this algorithm with some parameters. So this algorithm will give you the initial guesses, so approximately 2000 region proposals from an image. Okay, so 2000 region proposals, so 2000 windows of possible objects will be given to you, and then once you have that windows, you just need to crop the image in those windows and pass it through your CNN to predict the class and bounding box. Okay, so that's the idea. The same architecture we discussed earlier, we can use it on this particular crops. Okay, so that's the idea, and this is what we will be using. This library will be using to have these region proposals. That brings us to the very first CNN in this field, which is known as regional or region based CNN for object detection. More details can be found in these papers. I always encourage you to go through the paper. You should have the time to deep dive into these and then come up with better understanding on top of whatever I'm explaining. Okay, so first step, you have the input image. You pass the selective search algorithm which we discussed in the previous slide and generate about 2000 regions or 2000 regions of interest, you can say, or region proposals. So something like this, only few of them are shown here. So all these are different regions proposed by the selective search algorithm. Now what you need to do is you need to crop each one of them. So let's say 2000 of them one by one. So you crop, let's say this, you cropped it, and then you pass it through this particular CNN. The CNN can be anything. So for example, you can use a VGG16, or you can use a ResNet 50 or 18. So that will be basically some pre-trained network. So it will take this image crop. So this crop may be of size 224 cross 224. So originally it may be much smaller. So you are kind of resampling or resizing the image to 224 cross 224, whatever expected size of the image, and pass it through the CNN. The CNN will have one classifier head similar to what we discussed, and it should also have one bounding box head, right? So that is there. So these are the predictions. So for example, for this will be the coordinates if it is there. If it is not there, doesn't matter. If it is there, you will be worried about these coordinates. Okay, so that is the critical thing. So one important thing here is you resized or you cropped the region of interest to the size of your input. So then what you should also do is you should basically have a ground truth, right? Because you need to have a regression loss against these predictions, right? Whatever you're predicting, you should compare it with the ground truth. But the problem is these predictions are on this image, not on the original image, right? So you basically kind of cropped, or we call it at warped from the original image. So the prediction, this either should be matched to the original image. That is one way to go about it. But then you need to, because these predictions will change each time you run, each epoch it will have new predictions. So mapping it back to the original is not that easy. But the other way is much easier, because you have the ground truth. You kind of warp or kind of change the ground truth to these prediction coordinates. So this is very important. So you kind of translate and scale your original ground truth bounding box. Okay, so you have original ground truth bounding box, you translate and scale that to fit into your region proposal, because this is your region proposal. You may have a original bounding box somewhere, you just need to map it to this, so that that becomes in the same range as your original figure. Then you can compare whatever this prediction, you can have a simple regression loss of the translated scaled ground truth coordinates with this, right? So let me explain in steps. So during training, assume your region proposal is, let's take one region proposal, its bounding box are px, py, ph, pw. We'll go for the YOLO format. So px and py are the center locations of your region proposal prediction. This, of course, this is not annotated. Please don't confuse. This is the region proposal from your selective region algorithm. Okay, selective search algorithm. It will give you 2000 proposals. One proposal, let's say, this will have sender locations as px, py, its height and width as PHPW. Okay, so that's for a region proposal. That's your kind of the dimension that you're looking at, the space that you're looking at, right? And then your ground truth original, let's say it is at, for this particular object or the object we are considering, it is at GX, GY and GHGW. Okay, so this is your original ground truth which you annotated. Okay, that's your ground truth. Now what you need to do is, let's assume that the target prediction is TX, TY, TH, TW, which is predicted by the model, but this is in line with your cropped or region proposed. This is within this region, not for the image, right? So these coordinates are basically within this cropped or warped region. Now we need to do is either map this to the image space or map your ground truth to the region proposal space. So this one is easier, because otherwise you need to map it every time a new prediction comes. The ground truth is fixed already. It's not going to change epoch by epoch, right? Because it's fixed. So we'll go with this. We will map this ground truth to the space of your region proposal, which is this. So it looks like this. So your ground truth is going to be the center location will be kind of translated. So I'll have a demo, so it'll make you easier for you to understand. So you kind of map gx to the gx bar space. So this gx bar or gx hat space is very similar to this space, or it is in this particular space. It's you are moving from the original image space to the warped image space, because px, py, ph, pw is your bounding box within that interested warp region, right? So you just basically translate and scale it. You normalize by the width of your bounding box, not the image. And similarly, the gy, which is the center coordinate for the ground truth, this guy is, so basically you're moving the center point of your ground truth with respect to your original image to a center point with respect to your region proposal predicted bounding box. Okay, so that you can kind of do a regression later easily. So this is with respect to the coordinates, center coordinates, but with respect to the height and width of your annotation, the ground truth height was gh and ground truth width was gw. Basically the annotation box width and height, you need to scale it according to the height and width of your region proposal, which is actually doing here. You can just divide it and keep as it is, but you do a log compression. That is because the height and width is a very large value. So sometimes this gh by ph can be very small, sometimes it will be very large. So in order to bring them to the same figure or same range, we do a log scale space conversion. So it's just to compress your overall values. Okay, so that's a very interesting idea, because people started with just using gh by ph, but then they realized that these values will go from very low values to very high values, and that's really difficult for us to kind of tackle. So they introduce a log compression, which is quite a straightforward way to do it. Okay, so that's the idea. So log space scale transform is just to make sure all the values are within some small range. It won't kind of offshoot too much. Okay, so just to repeat what we are doing here, we take the image, we generate the bounding boxes through this region proposal algorithm, selective search algorithm, maybe 2000 of them. Each one of them you crop, pass it through a CNN. That CNN will predict the class and the bounding box locations. But these bounding box locations are not with respect to your original image, but with respect to your crops or your warp region. So then we need to basically do a small change. Your ground truth annotation, which was on the original image, you kind of warp it to the bounding box through these two operations. So your sender points are translated, so that is something like this. So you basically map it to your bounding box of interest, and the log scale, you basically scale up or down your original ground truth bounding box to your region of interest. So that's the idea. And then of course you can calculate the regression loss between your prediction, the model prediction T, and G hat, not G, because G was defined on original image. G hats, which we calculated here, is defined on the warped region. Okay, so this G hat needs to be calculated only once, because ground truth is not going to change while you are running the model. Okay, so that's the idea. And now inference is really not that trivial. Inference is take some step. It's same actually. You pass the input image to a region proposal algorithm. It will predict 2000 of them. You pass it through the CNN one by one. It will predict your class and your bounding box. Now these bounding box predictions are with respect to the warp region, but we need to map it. So this is during the inference I'm talking about. So this model is well trained now. So each of the crops, it will give you the bounding boxes, and these bounding boxes are with respect to the cropped region. You need to translate or scale it back to your image space. So we just need to invert the operations what we did in the previous slide. So it will be straightforward. So during inference, the model predicts this. Now we need to translate this into your original image space. So that is done just the reverse. Okay, so your tx hat is nothing but your tx into your bounding box width plus your bounding box center coordinate. So it's just, remember the previous case, we kind of did the opposite. We just subtracted these two divided by the basically tx minus px. You remember the gx minus px by pw is what we did. We just reversed it. So your prediction tx, you kind of scale it with respect to the width and translate it with respect to your bounding box prediction. Okay, so that's the reverse operation. Similarly, you do for the location ty to ty star. So ty is in your warp space, ty hat is in your original image space. So tx bar, tx hat, txy both are in your original image space, whereas tx and ty are in your bounding box or warped region space. Similarly, you do the scaling for the height and width of your tw and th. Okay, so that's it. So that's it. So pretty much kind of covering the region based CNN. So just to reiterate, you pass the input image, then you make predictions or region proposals through the selective search algorithm, then you crop the image for all these region proposals, you pass it through the CNN. That CNN will predict the classes and the bounding boxes, but there is one problem: these bounding box predictions are with respect to the warped region, not with respect to the original region. So during training, you translate and scale your ground truth annotation to the warping region based on the formulation we discussed last slide. During inference, you scale your predictions which are in the warped region back to the original image space using the inverse formula which is listed here. So it's not straightforward, but not that difficult as well. Okay, so now one problem, you have 2000, let's say during inference you have 2000 region proposals, so that means 2000 predictions you will have. But that is too much, right? You have to reduce the number of predictions. How to do about it? Many ways to go about it. You can use the classification score, because each bounding box will have a classification prediction, like 90% sure that this is a dog, or 75% sure this is a dog. So one way to do is very trivial way is like you put a threshold and reduce all those bounding boxes with a lower accurate or lower confident predictions. That's one way to go about it. Another way is like you kind of iterate over each class. Let's say one class, you iterate over each of the boxes for that class and remove the boxes which are kind of not useful. How to measure that usefulness is what we are going to do. So there is a measure known as intersection over union. So all these we will discuss very soon. So intersection of or union is kind of finding the similarity of one bounding box with all other bounding boxes. So you can do something like this. You do take one class, all the bounding boxes belonging to that class, then you kind of do a intersection over union across all the bounding boxes. If very high value of IOU means they are very similar, and you can discard some of those very similar bounding boxes. So we'll go through that algorithm in detail. Okay, so that's the idea. And then there is this performance evaluation. So how to do it? So for classification, we know the performance evaluation will be in terms of its accuracy, or more clearly in terms of its precision, recall, or sensitivity, specificity, which you can derive using the confusion matrix through the true positives, false negatives, true negatives, and so on, right? So similar kind of concept is there in object detection, which is known as mean average precision. Okay, we'll discuss that very soon.